Okay, I'm Giorgio Grioli. I'm going to talk about variable stiffness actuator from the user point of view. So you have seen this slide from Alessandro's presentation, which introduced you to the evolution of actuation from rigid actuation to variable stiffness. And we are going to follow this evolution a little bit closer than what Alessandro did. So let's start from a rigid servo motor, which is one of the most common type of motor used in rigid actuator, and see how it's made. It is the parts that compose this are one electric motor with the gearbox and an output shaft. This is the real fundamental parts of a servo motor. I mean, you have this electric motor, which, as probably you know, it turns a lot faster than what you need, and with a low torque. So you use a gearbox to move an output shaft with it, which is usually connected to the link of your robot. But other important parts are the sensor and the control board that you can find on your servo motor. With this sensor, which are usually position sensors, and the control board, what you can do is you can close a control loop. What actually happens is that the servo motor itself closes its control loop, so that what you get again is a control input. So you talk with this device with a digital protocol, and the device implements what you ask him. This kind of device, as you probably know, are designed to be fast, precise, and very repeatable, and so they are rigid by design. The more rigid, the better the device. As I was saying, they close an internal position loop so that you command a desired position, and you have that the actuator follows this desired position, almost transparently. They are very easy to use and very accurate, and because they behave essentially as position sources. To some extent, you just can assume that the position you command is the position that you get out. And this is fine, but what was not always nice is that when position sources don't handle nicely the constraints, for example, if you have that the joint cannot go over some limit because, for example, there is a wall or there is a limit on the joint, or you have contact, you have that bad things happen. You have that if you command a desired position which is over the limit, usually you get very high contact forces which can bring to damage, which can be dangerous for the device, for the environment, for the people. You can burn the device if it doesn't have fail-safe protection, for example. Then another kind of rigid robots, which are more recent, is torque-controlled servo motors. Now that you can find on the market servo motor which include torque sensor. They are not that common, but they exist. And with that, you can close the loop, no more on the position, but on the torque. And what you get is that you command them a desired torque, and you get in the output that the torque applied on the load follows the desired torque. They can be used to implement advanced control strategies like impedance control, and they have a nicer behavior, especially in slow interaction tasks. But the problem with this kind of device is that they use the same actuation technology on the low level. So the system, in reality, is still rigid. So the fast interaction are still problematic. If your rigid robot, even if torque-controlled, hits a wall, the time that takes for the controller to react to this hit could be dangerous. During that time, the system is perfectly rigid. So it doesn't change much the fact that you use a torque-controlled robot. Also, because of this, it's the third step, the third stage of rigid robots, which by some extent is the first step of soft robots, is rigid robots with soft add-ons. An example of this is the use of remote center of compliance, like this one. They are used in a large number of industrial applications when you need interaction and you have uncertainties. Or another idea is to use a soft cover for the end effector or for the arm, for example, to be less dangerous to people. The natural evolution of this, as you know, is soft actuator. Soft actuators are now a standard in research, and there are already early industrial products. You know that Baxter, who was launched 2 years ago, is being sold around the world, and also KUKA lightweight robot, to some extent, can be seen as a soft robot because it has harmonic drives, as Alessandro was saying, and so somehow it has physical stiffness in the system. What is the difference between what is the first kind of soft actuator that existed? The first kind of soft actuators is series elastic actuators. In a series elastic actuator, you have a standard servo motor, which is connected through a spring to the real output shaft. And then you have another sensor here on the output shaft, so that you can measure the position both here and here, and through the deflection, you can reconstruct the torque. This allows you to perform the same kind of torque control that you can do with the torque-controlled motor, and it also has the advantage that since the spring is real, the spring is physical in the system, when you have fast interaction, the system behaves as if having a spring inside, not as if it was rigid. As I was saying, these are the advantages of the system, but the disadvantages are that the system, with the link inertia, determine a natural oscillating frequency of the system. And this somehow is a limit to the bandwidth of in practice, it almost always is a limit to the bandwidth with which you can actuate the torque on the output. And this ultimately limits the performance of the control that you can get. That's also why, because variable stiffness actuators were developed. Variable stiffness actuators are now in an advanced research stage. They are out from more than 10 years. And there are a lot of solutions which were studied and developed during the years in, really a lot of different ways to implement variable stiffness actuators. And they are starting to go out from the lab of who created them toward the lab of people who can use them. An example here is, this is one of the very first kind of actuator, is the AMASC from Hurst and Migliore. It was created to make a hopping leg, while here you can see the DLR hand arm system, which is all made of variable stiffness joints. So, as I was saying, the motivation behind the development of this is, since the stiffness limits my bandwidth, and since my bandwidth requirements depend on the application. For example, they can be low when I have hits, and so I want to absorb inputs, but they could be high when I want precision or when I want fast acceleration and deceleration. The best solution would be to be able to change the stiffness, and that's what led to the development of variable stiffness actuators. So, a first definition of variable stiffness actuator, which is a first approximation, but it explains the idea very clearly, is that a variable stiffness actuator is a serial elastic-like system where you can change the stiffness that is in series with the system. We will talk a lot about variable stiffness actuator, all this talk and most of the talk of this school are about this, but since we're looking at the landscape, let's keep doing sightseeing for a little. The next step of soft actuator is variable impedance actuators. So they are in an earlier phase, and they are a really hot research topic now. Here, for example, you can see the variable physical damping actuator developed at IIT, which is a device which instead of changing stiffness, changes the damping, which is in parallel with the spring. And changing the damping is really the very next things that comes in your mind when you want to do this. Then there is also the possibility to change the inertia. There are mechanisms like this that are used, for example, in the field of energy harvesting, like systems like the Kurtz and also high-efficiency flywheels, which are now becoming a reality for storing energy. And also, strongly nonlinear series elastic actuators are usually put in this category because even if you don't control this change in stiffness, their stiffness changes a lot depending on the external load which is applied. And also now the more recent kind of development on this field is the multiple parallel approach, or series parallel elastic actuator, in which you have the stack of various actuators and spring, which together move the same load. And then the step which is even further, which is also another very hot topic in research, is this robot with soft structure. So you have a robot in which the softness is distributed along the robot. You can have, for example, soft joints, like in the PSI-IT soft end, where you have that each joint is made of a small part which is flexible in several directions. It's continuously flexible. So it's not simply an elastic joint as a series elastic or a variable stiffness joint. Or you can have robots which have soft links, for example, like this one, in which you have that the joints are, in first approximation, you could say that these are rigid joints, but the robot itself has a flexible structure. Or the more extreme approaches go toward soft bodies, in which everything is flexible in the robot. For example, in this kind of robot worm, where both the body, both the link and the actuator, and also the structure of the actuator itself is soft, it's elastic. I mean, here everything is made of soft silicon, and the robot moves by pressurized air, like this one. Okay, so let's go back to the variable stiffness actuator, which are our main topic. My last definition of a variable stiffness actuator is that of a SIA, in which you can change the stiffness online. But what if we want something more precise? Well, something more precise, even if you have this cloudy stuff here, essentially this is a very generic definition of variable stiffness actuator, which accounts for a lot, if not all, of the prototype existing. Variable stiffness actuator is a mechanical system which has 3 bodies, so 2 motors and 1 link, and connects them through an elastic transmission system, which in general is nonlinear. So if we look at the dynamics of this, you have that it can be defined, this is the more generic form you can have. So you have you have a part here which is the dynamic of the robot that probably all of you know, where Q, so is the first state Q is the position of the links of the robot. And then you have an elastic function, UQ, which depends on the position of the robot and on the position of the 2 other motors, plus the eventual external forces acted on the robot. Then you have other 2 equations which are similar, and they are the dynamic equation of the 2 motors. So you have that this is the first and this is the second. They have the same form, although depending on the device, this part here could be very different, and also the sides of the 2 motors could be very different, where here you have the 2 inputs. And also you could have at least in principle, you have also the dynamic of the actuation. For example, this is the dynamic of the torque, which comes from a DC motor. And here you control the voltage of the 2 motors. Okay, I had it. Usually the electrical dynamics is neglected because it's much faster than the rest. So what you get in the end is something like this. It's a system which has 2 inputs, tau 1 and tau 2, which are the torques applied by the motors on their axis. And then you have 1 disturbance, potentially, which is the external torque. And then you have a configuration space, which is determined by Q, theta 1 and theta 2. So it has size 3, while the inputs are 2. So the system is underactuated. This is very important, and you will see in the later lessons that this is what causes much of the difficulties in controlling variable stiffness robots. Okay, another important part is that these 3 here are the elastic torques. So these 3 functions model the non-elastic transmission, the non-linear elastic transmission, sorry. And all these 3 functions are partial derivative of an energy function U, which is defined on Q, theta 1, and theta 2. So you have that the force on the link is the partial derivative with respect to the Q, and the force on the two motor is the partial derivative with respect to their angle. And also you have that the second derivative on Q, U, Q, Q, is by definition the stiffness on the output, which is what we want to control with the variable stiffness system. So let's look also a little in the categories of variable stiffness actuator, but from the viewpoint of equations. So one system or one category of variable stiffness actuator is the explicit stiffness variation actuators, which are somehow the more similar to the original idea of the variable SEA actuator. So you have a big motor that controls the equilibrium position of the system, like it was in the SEA, and then you have another motor which somehow changes something inside the spring so that the stiffness changes. This translates in that you have that U changes its shape and becomes like this. Instead of being a generic function of the three parameters, you have that U is a function of the displacement between Q and theta 1, because essentially theta 1 is the equilibrium position of Q. Another type of variable stiffness actuator is the agonist-antagonist variable stiffness actuator. For example, here you see the VSA1 that also Alessandro showed before, in which you have two motors, one here and one here, which through a nonlinear transmission, which is made by this belt on which some springs act, moves the link here. So in this device, you can see that you have both of the, since the system is agonist-antagonist, you have that both motors contribute on one side to the motion of the link and on the other side of the stiffness of the output. And you have that this translates in the equation that the function becomes function of the two displacement. So you have theta 1 minus Q and theta 2 minus Q. Another specialization of this kind of actuator is the decoupled agonist-antagonist VSA, in which you have that the two, essentially you can separate these two functions, and you have that the function acting on the links is simply the sum of the other two. So this is, what you have here is that each motor acts on the system through a separate spring. So it's like having two motors in parallel, two motors and a spring in parallel acting on the link. So you get this on the equation. And examples of this are, for example, some couples of muscles in the human body, like the biceps and the triceps, if I'm not wrong, and also the QB-Move, which is the device that we will be using during the demos. So let's make a snapshot of the landscape. We have rigid robotics again. We have soft robotics, in which you can have soft effectors or discretely soft or continuously soft. And inside here we have soft actuators. And among soft actuators we have series elastic and variable impedance and variable stiffness, which is one of the family inside. Sorry, it moved. Okay, so within variable stiffness actuators, we have a variable series elastic, agonist-antagonist, in which you have coupled, uncoupled, and also monodirectional uncoupled, which I did not introduce, but essentially are a system in which each motor can only pull on the link, like on muscles, for example. But there are also hybrid systems in which all these principles are mixed, and so you cannot specialize the functions as we did before. You can also categorize VSA based on the working principle, and you will be seeing this in the lecture that Professor Vanderbocht is going to give tomorrow, depending on the way it works, if it works by preloading a spring or by changing geometry, but I will not stay on this. So you have that, we have really this roadmap of how soft and rigid robotic works, and if you're a little bit lost, you are here. So we to avoid being lost, that's what happened to us, that we're developing the technology some years ago. What we did is, okay, let's look at this from another point of view. Let's try to use the user point of view and to sort out what these systems are. And that's what we are going to do now. So our golden rule would be to try to do an abstraction. We will want to consider the system as a black box model. So we want a system in which we have a mechanical interface, again, in which a position and a force are collocated. So you have that the position of the link is determined by the balance of the tau from the outside and the torque from the inside. And we have two inputs that that following the lesson of Alessandro are, for example, the equilibrium point and the and the co-contraction, let's say. So we want to characterize as a first step the physical behavior of this kind of system. And so we want to look at the performance parameter of the system. So what are the performance parameters of a VSA? To understand this, we will look at the basis, and we will start from how to choose a motor for a normal robot, how to choose, for example, a DC motor or something else. Well, if you wanna choose a motor for your robot, you have to decide the first thing you could think about deciding could be technology. I mean, there are electromagnetic motor, piezoelectric, electroactive materials, pneumatic, hydraulic. There's really a plethora of system of technologies that you can choose among. And you have, for example, that these kind of systems are costly and have low power density usually. And the other two here are noisy, for example. And the hydraulic is very high power density, but it's usually dirty and dangerous if you're not careful. So, I don't know, but let's stick with the electromagnetic, which is what most people choose usually. If you want to choose electromagnetic, you have a lot of possible systems, but usually in robotic, what most people use is brushed or brushless DC motors. And you have that the brushed DC motors have a good power density, and they are really easy to drive. I mean, it's the simple kind of motor that you know about. While the brushless motors are lighter and need less gears, because usually they are designed to apply a higher torque without reduction. But on the other hand, they need more electronics. And I mean, they have the best power density, but they're usually more difficult to drive, and you're probably ending with more cumbersome boxes, to say it with easy words. So, but to avoid getting lost again, instead of taking another map, looking at the technology is probably not the very right thing to do. The right thing to do is to look at the power of the system. When you want to choose the motor for what the application is, you have to define essentially what is the continuous operation requirements and the peak operation requirements of your system. For example, if you have an industrial device like a lathe, you have that it's turning all the time at the same speed, so you have a very precise regime at which you are working. Or otherwise, if you design a robot, you have a lot of peaks. For example, think about a pair of legs. Every time the leg stands, it's exerting a lot of torque, and while it's in the air, it's not, for example. So instead of looking at the technology, let's look at the power. How do I look at the power of an electric motor, for example? Okay, let's take the torque speed characteristic. A typical torque speed characteristic of a DC motor is something like this. So you have this line, which goes from the stalled torque to the no-load speed. It's somehow the very first thing that tells you how the motor behaves. You can have that this line has different slopes, which depend essentially on the number of windings on the motor and how it's made and the kind of magnets. But it tells you which is the maximum theoretically acceptable torque for the system, and which is the maximum speed at which you can expect it to turn. Then you can have two kind of limits on this torque on this plot. For example, you can have, not always, but sometimes you have it, a maximum torque limit, for example, to gearboxes, if you have them. If you, for example, use harmonic drives, sometimes you happen to have this kind of cut on the motor. Then you have another limit, which is thermal, which is something like this usually, which cuts away one of this zone from your graphic, from your working area. That is that you go over some line, your motor is gonna hit and then burn after some time. So you can go here, for example, for peak operation, but you cannot think about staying here for long times. And then you have what remains here, which is the continuous operation area, which is what's interesting for you to take the size of your motor. So again, power. So power is torque times speed. Let's not forget about gearboxes. I mean, the same motor with different gearboxes can have very different plots, which have the same, I mean, the power of this is the same, but you have a very different shape for this space here. So, for example, you have that if your application working area is like this, and it doesn't fit here, you could simply have to choose a higher gear ratio, and so to make it fit on your system. This is an error that usually new students do a lot. If you ask them to choose a motor, they just take the electric motor without putting any gearbox, and they tell, oh, I need an enormous motor. No, you need gears. So let's go back to VSA. What are the main parameters of a VSA? So a VSA is primarily a motor. So we still have the same figures of merit, which are torque and speed. But variable stiffness actuator is, one of the core characteristic is the variable stiffness indeed. So we also have to look at the stiffness range of the system. So again, for the torque and the speed, we have the same old story. We have this kind of curves, which is limited by friction, motor power, and all this stuff. But for the torque versus stiffness, we have that the stiffness range in general is affected by the load. This is almost always true if the system has nonlinear springs, for example. You have that the more you load the springs, the more the system stiffens usually. And this is very important because it has also to be accounted for when you are controlling the system. Then what you have is that the speed and the stiffness range have to be combined, because this plot here tells you that essentially when you are running at some speed, you are cutting away a part of, you are using part of the torque to fight the resistance of the motor. So you have that you lose part of the torque, and for the system, it's almost like you have that the torque you lose here is like torque on the external side. So you have that the system shifts here due to the fact that you are running at some speed. And what's real is that this is not as simple as I told you, but this is a three-dimensional working volume. I mean, what you get is that speed, torque, and stiffness range are conjoined together in some complex shape that you have to account for. So when you want to choose, want to characterize your application, you have an application working volume, which is defined in terms of speed, torque, and stiffness range, and you have to fit this inside the volume of the actuator. This is essentially the base decision that you have to make when you want to choose a variable stiffness actuator or another. Then another important aspect is that stiffness has a speed too. So somehow that the real figure of that would be four-dimensional, but it's difficult to visualize and to work with. And what we usually really care about is the time to change the stiffness. So again, this could be, in general, this time could be different when there is a load and when there is not. So the best way to characterize this for a variable stiffness system usually is with two numbers. So it's the nominal time to have the highest change in the stiffness, from the minimum to the maximum, or from the maximum to the minimum, depending on which is worst. calculated with both with no load and with the nominal load applied on the system. And this is very important for the rapid task execution. For example, for the bang-bang optimal control that Manolo is going to explain on Monday, you have that sometimes you assume that the change in stiffness is instantaneous, but it is not. So you have to account for these times when you do your experiments. Also, other important parameters are related to the elasticity. Elasticity means deflection. So variable stiffness means variable deflection. So what you need to know, because it's a matter of robustness of your control. For example, if it's important to know where your links are ending if you have an external torque, is the maximum deflection that you have with the different values of stiffness. So you have that, for example, with the minimum stiffness, you can have that your link can move 30 degrees, while with the maximum stiffness it can move just by 2. I don't know, they are just numbers, but they are important because they change how the system physically behaves when you use it on a robot. And also elasticity means storable energy. A lot of nice applications that you can think of with soft robotics are related to the absorption on impact, for example, of to exploit natural oscillation or to, I don't know, to optimize cyclic motion. And in this kind of application, it is important to know what is the maximum amount of energy that you can store in the springs. And this is the number which is reported. If the spring was linear, you could just use this kind of system. But since in general this kind of systems are non-linear, it's easier to have this number already calculated for you. So these are the most important figures of merit that you have to care about. What follows now is detail, as I say in this slide, but sometimes the devil is in details. So it's better to keep looking at it. Another aspect which is important, it's the active rotation angle. I mean, not all of actuators can rotate continuously. If you take an electric motor, it can rotate continuously, but if you start putting sensors, springs, and stuff, this could be not true anymore. I mean, I don't know if you have practiced using the toy servo motor, which are used for RC toys. They cannot rotate more than 180 degrees, for example. And this is due for them essentially because of the sensor that they are using. But in variable stiffness actuator, there can be other limits depending on the type of transmission and on the shape of the system. Also, if you think of a highly optimized joint that could be integrated, for example, in the elbow of a robot, the amount of rotation angle could depend essentially on the shape of the system. Since the main application of this kind of devices is robot joint, this is usually not a problem, but for some applications it could be. So in general, you should check that the range of the active rotation is enough to perform the task you want. You have also to account that this is the active rotation angle, so the rotation angle of the equilibrium point of the spring, at which you have to superimpose the effects of the deflection. Then another aspect which is important, especially if you want to do something which has precise torque or position control, is hysteresis of the system. Since this system is flexible and since it's real, so it has friction, what you get is that if you do load-unload cycles on the system, what you get is that you get some amount of hysteresis on the system. So you probably know what hysteresis is. It's simply that when you load the system, it moves a little farther on one side, and when you unload it, it moves on the other because some of the energy is lost due to friction. So it can be, this hysteresis, it's better to know it with plots. So, but a simple way to quantify this can be in terms of torque. So that is to say, you take the larger section on this family of curves on this direction, or in terms of degrees. So that is taking the maximum number in this direction. And then other aspects that are important for the application that you want to do is the transducer that you have on the system. So usually this kind of actuator, which are highly integrated and are very high technology, at least have an output shaft sensor to measure the position. They could also have, for example, a torque sensor on the output. The most advanced kind of device have them. Or they usually also have another two sensors which are on the position of the motors, which are needed for torque pilot control. So a nice characterization of this device, of a variable stiffness device, should provide also you the map of the sensor, where they are and what they measure, and if they are absolute, if they are relative, and what is their resolution, for example. And then another very important aspect is the fact that since you are looking at this as a user, so we are looking at this as a component, what we should rely on are interfaces. So interfaces are very important because it's what we assume for granted, and it's what we take to design what's around our system and to integrate the variable stiffness device in the rest. So the interfaces are defined essentially by the mechanical interface, that is the drawings. They are there and you have to respect them. And also the drawings and the specification of the electrical interface, for example, and the protocol of the communication, simply. So we've seen a lot of different parameters of a variable stiffness, but we can imagine that we can go much deeper in the detail. And when can we stop? So how deep is deep enough? Well, one thing that is left to see to determine how deep is deep enough is the different control approaches that you can have on variable stiffness actuated systems. Not actuators, but systems, robots. You have essentially a variable stiffness actuated robot. It's made by a robot and a series of variable stiffness system in which you have other motors and the springs. And then this robot is interacting with the environment, and this robot will have some sort of centralized controller. So you can have that the approach with which you control the VSA could be decentralized, as here. So you are trying to make the centralized controller the simpler it gets, so that it behaves somehow just like a task controller. You control the things just from the higher level, and you have that each VSA behaves as a servo system. So you have a decentralized controller on board of the system, which could be, I don't know, observers and stuff. And essentially what you give, the task controller gives to the decentralized controller some reference behavior, which could be expressed, for example, in terms of reference position and stiffness, or it could be the speed and the torque. I don't know. It could be a lot of different way to define this. And then this decentralized controller takes the burden of controlling the servo VSA. This kind of approach has the pro that is distributed, so it's more component-oriented, and it uses less resources on the central intelligence of the robot. But the disadvantage of this kind of system is that it will ultimately be less optimized of what you can get in another way, which is a centralized approach. In the centralized control, which can be fully optimized to take the best out of your system, what you essentially do is that you command the torque to the motors from your centralized control, and you optimize. You do the control from the highest level to the lower level, all centralized. You have to. The disadvantage of this is that you have to go through a lot of details and to take care of a lot of things that you probably don't want to take care of usually. So if you can, the best way to go is to use decentralized control. So why? What are these details that you have to go through? I mean, essentially, is the nonlinearities of the system. As I told you before, most of the variable stiffness actuators rely on nonlinear transmissions, nonlinear springs, so they are, that's why they are more difficult to control. And another problem, which is something that Fabrizio Flacco will talk about on Tuesday, is that one of the, let's say, shady concept here is that what is stiffness? Stiffness is a differential quantity, so it's difficult to measure for real. It's not something you put a sensor on. And that's why it's difficult to make a feedback on this. And it's better to make it centralized to some extent. Decentralized, sorry. So I mean, if you have a black box VSA, it is good for cooking, so you can use it as a component. You can get it prepared by others, so it's ready to use. And the con is that you have to adapt a little the recipe, so your robot, to the ingredients, so your actuator. But the disadvantage is that it's not as easy to control. I mean, to achieve top performance with the black box robot, you have that the optimization requires very fine calibration, and the real optimization often requires customization of the device. So, but this is for everything. I mean, if you could, you would choose your perfectly exact DC motor, but you have those on the market, no? So, once again, how deep is deep enough? Do I want to keep a black box, or do I want to open the box? This depends essentially on how demanding is your task. How much do you need to optimize your performance? So if you want to do all of this, it means that also the answer to this question here is yes. So you really need a mathematical model. So again, what is the mathematical model? The mathematical model, which is practical to use, is based on a small set of functions. The first of all is the recoil point function, which is what we called before equilibrium point. This function, which is usually can be simple. For example, can be the average of these 2 points here. But in principle, it could be not. I mean, especially for the hybrid system, this can be a very strange function. So you have to provide it to the user. Otherwise, it wouldn't be able to use the variable stiffness actuator. You have the equilibrium of the system depends on the position of the 2 motors, but you don't know how. And then you also need the energy function, which is the function that you use to derive the output torque function and the output stiffness function. So it's the function I described before. And also you need the spring torque function, which is the U theta 1 and U theta 2, which is something that you will need to do a fine control on the side of the motors. So we have looked a long list of parameters, but what we ask now is, where do these parameters come from? How can I extract all these parameters from a variable stiffness actuator? What I can do is it's an experimental characterization of a VSA. So we are not going all through the experimental characterization, but there are a couple of very basilar and fundamental tests that you can make on a variable stiffness actuator to characterize it. One is the quasi-static load and load cycles. So you fix a stiffness preset, for example, and you load and unload your system with an experimental setup, which can be something like this. You put a mass that you know at a given distance from the joint of your robot, and you move the link from position 0, that we'll call this one, to 90 degrees and back and forth, back and forth. With this, what you get out is essentially these hysteresis plots that I presented you before. These are real experiments plot for an actuator which has been developed at DLR in Germany. And you see that here you have the deflection, the passive deflection, that is the position of the link minus the position of the equilibrium. And here you have the torque of the system, which you can easily extract from the gravity function that you know. And these curves give you, for example, the hysteresis already, but you can distillate them to get nicer, smooth curves, which are the deflection torque curves, which you're going to derivate to get the stiffness. So that's how you get, from that plots, you get the torque deflection characteristic and then the torque stiffness characteristic. And from these plots, you get the maximum deflection, the maximum minimum stiffness, and the hysteresis I was saying before. Then another very important thing that you need to do is the step command. You give the system, you make the system execute two kinds of steps. In one experiment, you put the system in an horizontal configuration with no load, and you give it the largest step you can give him. In this way, you can extract experimentally the maximum position and the maximum speed of the actuators. And then another thing that you do in this configuration is you give him a step from minimum to maximum in stiffness. And from this second step here, you get the worst, you do it from minimum to maximum and from maximum to minimum, and you get what is the time needed to adjust the stiffness. And then you put it another time in vertical configuration, you put a nominal load on it, and you repeat the experiment for the stiffness. So with this experiment, you extract the maximum and minimum stiffness changing time with the nominal load. So this is the kind of responses that you get. As you can see, you can have a little oscillation. It changes a lot depending on what system it is. This is again the system from DLR, and this is a link step response to the first experiment that I described. So you have the output position and time here. While this is the time to change the stiffness, the stiffness percent. So you see that the two curves are slightly different because the blue one is made with the nominal load and the red one is made with the no load. For example, in this kind of system, you have that. The behavior of this system can be very, very different because they are nonlinear and they can be very strange. Here you have that the system with the nominal load is faster to change the stiffness than without the load. Usually, for example, in the cubes that we were using this afternoon, it's the converse. Usually you have that with no load, you have a faster time to change the stiffness, while when you have a load, you have a longer time. So now that I have all these parameters, how do I put them together? Well, this is all these parameters in reality are the fruit of something that we did in a project that ended some years ago called the Actuators, and now we are bringing on in Safari, which is a 3-page template which is designed to collect all the plot time parameters that we have described. You have on the first page, you have the main characteristic, and it's the kind of page that you would like to see when you have to choose the motor. This is like the first page of a book. Then on page 2, we have some more complex details, for example, the hysteresis and the 3D volume, which are not as intuitive. And also we have the map of the sensor and the description of their performance. Then on the third page, you have all the mathematical description of the system. So you have, for example, two small schemes that describe the macroscopic layout of the system. For example, here you have one of the motor, the other motor, and the output, and then also the principle on which the springs work. And then you have all the function that you need to formalize your system and put it into operations. As an example, we are going to see the QBMove datasheet, which is the system that we are using later. So let's give it a look. So as you see here, this is the picture of the system with the mechanical drawings on the sides because it's near. And then you have we start with all the operating data. So we have that the continuous power of the system is 4.8 watts, and we have a nominal torque of 1.2 Newton meter, and a nominal speed of 4 radians per second. Then we have a peak torque, which is 1.5, and a maximum speed, which is 9.5. As very similarly to what you would find on a simple DC motor. And then we start having the parameters related to the stiffness. So we have the maximum stiffness and the minimum stiffness, which come from this plot here. So you have that the minimum stiffness corresponds to this point, while the maximum stiffness corresponds to this one. This is the plot which relates the torque and the stiffness of the system, which is one of the most important and one of the easiest to read. So you have that the stiffness range of the system is this without load, and you can see that as the load goes on, the characteristic of the system, the range of the system shrinks and shifts toward higher stiffnesses. This is related to the shape of the nonlinear springs of this kind of actuator. So if you have different nonlinear springs, you can have different shapes of this function. Even if for example, all agonist and antagonist actuators usually have this kind of behavior, in which you have a larger range here, and then the range shrinks and goes up. And from here, again, you get this data. You also have the active rotation angle and the maximum deflection with the maximum stiffness and minimum stiffness. For example, when you have maximum stiffness, you have 9 degrees of maximum deflection, while with minimum stiffness you have 36. The active rotation angle of this system is 180 degrees because of the components that are inside. And the angular resolution of the output sensor is it's 360 degrees divided 32 and 68. This is 2 to the 15, because we use a magnetic sensor inside this kind of device. Then we have the electrical characteristic of the system. So you have the nominal voltage and the nominal current that the system absorbs when it's in nominal working condition. And then you have the peak current that the system will absorb when it's in peak functioning condition. And also here you have some information related to control. So it's the power supply of the control, which in our case is USB, and the nominal current driven by that port. Also, we have the I/O protocol, which is based on RS 485 over USB. Then we have a schematic of the electrical connection, which is explained more in detail in the manual, of course, but here it's on the data sheet. And then we move to the second page. Here on the second page, we have the experimental torque deflection characteristic, in which you can see that the system is not perfect. You have this kind of you have this hysteresis, and also you have some sort of rippling here. You see that this hysteresis changes a lot also on the different stiffnesses. For example, you see that it's lower with the low stiffness, which is the blue curve, and it's also low with a very high stiffness, while it's a little higher in the average values. And to characterize this it's very difficult. I mean, it's not something that it's easy to predict, because it depends a lot on the actual friction inside the system, for example. Here we have that the torque speed stiffness workspace, which has this shape for this system. You cannot see that the triangular form of the torque speed characteristic, because the motor that we use make this sort of trapezoidal form very it's a lot slanted. It's not slanted a lot, so it's very similar to a rectangle, for example. And you see here a map of the sensor. We have 3 sensors of position. There is the main sensor on the output and 2 other position sensors on the output of the 2 motors. And also we can sense the current that is going through the 2 motors, and the voltage which goes on the port. Okay, here we have other information about the connection system, which didn't fit on the first page, but are still interesting. For example, here these are the snap-on flanges that we use, which are made to make easy and fast prototyping. And then if we move to the first page, to the last page, sorry. Here we have a hint on the layout of the system. So again, here you see that we have the system is made of two motors, one on the right and one on the left, which are both capable of pulling and pushing on the output shaft through non-linear springs, which are this triangle, and the spring is made like this. So it's not much different from the VSA and VSA1 that we have seen before. If you remember, you have that a tendon, in this case, not a belt, goes through a spring which is pulling, and you have that if you pull both of the sides here, you have that the tendon straightens, and so the ratio of transmission from the spring to the system changes, and the stiffness changes by consequence. You have here that all the mathematical model of the system. So you have the equilibrium point, that is the average of the two motors, and we also have the output stiffness, the output torque, and the elastic energy, which can be defined like this. And these are typical parameters that we have found on one of our devices. Okay, these are some information, but we don't care about this. Okay, let's go back here. So all of this is going to be published soon on HIRR, on this paper, which is VSA from the user point of view. And okay, now that I have all these parameters, how do I use them? Well, I will leave you these two exercises, which are very, very simple. And they are listed on the paper, so if you download the paper, you already have the solution, but please try to do them yourself if you have time. So we want to design a system which is like an oscillating saw, which is powered by a VSA system. So let's imagine that this spring plus a reference here, it's a variable stiffness actuator, and this is the tool head of our automation system. This system essentially has to cut some material by punching it with this blade several times, and we have that the stroke of the cutting blade, so that the amount of penetration of the blade is A. We have that the force, the average force to cut the material is F, and we have that the inertia of the tool head, depending on the application you want to do, oscillates between I max and I min. And also we have that the speed at which we wanna move our tool head is omega. So given these four numbers, try to guess what is the working volume of a variable stiffness that you will need. A second exercise is again on the paper is based on hammering. So this is not something that I will ask you to do now, because this is more related to what Manolo will present on one of the next sessions. But the idea is again the same. So you have a variable stiffness actuator which moves an hammer, and this hammer has to drive a nail into some surface. So we would want to minimize the number of hits that are needed to drive the nail in the wood. So after you listen to Manolo's lesson, try to guess what is the need for this kind of application. So if there are any questions. Oh, okay. No, okay, this is interesting. Let's go there. Yes. Yeah, this is the... no, it's right. It's not written. You are right. This quantity that goes from... what is constant is this is the amount of stiffness that you have here. So this is 0%, which is the minimum, and then you have 25 and 50, and then 75, and then 100. And what is constant on this line is the internal stiffness preset, which is defined as the difference of position between the two motors. So this percentage is on the stiffness range at no load, and then starting from that configuration, we keep it constant and we increase it. Yes?
So does that mean that by setting that equilibrium point?
Yes, here we change the equilibrium point, yes.
So 0, 25, 50 are related to equilibrium point?
No, it's not the equilibrium point. This is the point, it's the other input. It's exactly the constant, not the equilibrium point. This is the input that controls the stiffness. For example, in this particular device, the equilibrium point is the average of the two motors, while this input is the difference. So it's if the two motors are like this, you have minimum stiffness, and if you open one with respect to the other, the stiffness increases. So in this case, this is the angle of difference between motor 1 and motor 2. So it's the amount of it's the input that controls the stiffness. Yes?
So I see there are no torque sensors on the actuator.
Yes.
But is it possible to estimate from the current?
Yes, you have the currents. It's the current reading are not always so linearly related to the torque, but it's something you can use. You can estimate the torque from the model of the stiffness. They are both estimates. Probably the better way to do would be to make some Kalman filter, sort of integrate all the information. Yes?
How do you measure the stiffness?
Where? You mean here or?
Yeah, for example, here.
In this experiment, okay, let's go back to the presentation. In this kind of experiments, for example, to characterize the system, so when you do it once, when you do it offline, we measure it from this. So you get this hysteresis profile, and then since we are who built the device, we know the model that is behind these lines, so we do a regression on the model on this, and we do the derivation. So sometimes we did it using the model of the system, on which we designed the system, and sometimes we do it just by filtering the data, because we have to take derivatives, so sometimes it's noisy, but essentially all comes from these plots here. Then there will be a talk by Fabrizio Flacco on the last day, which is about methods to estimate the stiffness online, which is another option. I mean, when you want to do control of the stiffness, since you don't have a sensor, what you do is usually you rely on the model that you have. For example, so this kind of function. So you measure the three position and you have the stiffness. It's a function of them. Or you can use a stiffness observer. There are several approaches in literature, but this is still an open problem. So I also did some works in the past year, because it's really an open problem still, to make a closed loop control of the stiffness, which is based on the stiffness and not on the model.
What is the most reliable way to estimate from the data that you observe, or like this?
It's an interesting question. If you estimate it online, you're doing it online. So if you have a variation on the system because, I don't know, for example, the springs change because of heat or because of use, you're still doing it online, so you follow the estimation. But doing it with an estimator is not easy. So Because essentially, since stiffness is a differential quantity, you have to relate the variation of position with the variation of torque, and this is not easy, because essentially when you don't have a variation of the two quantities, you are blind. So there are in literature, I'm sorry, I will burn Fabrizio's lesson, but in literature there are approaches in which you have no model at all, and these approaches are more sensitive to the fact that you are blind, where you don't have, but the quantities don't vary. And there are hybrid approaches which use the model and build an observer over them, which are more robust.
Does that mean that if your actuator doesn't move, you cannot estimate its
Yes. Can you repeat the question?
does that mean that if your actuator doesn't move?
Yes, you cannot. If you turn it on, and it's the first time, you don't know what stiffness is. I mean, unless you did the identification before, you know what you hope the stiffness is. I mean, from the model and from the parameters that you estimate or you guess, depending on, you can make an estimate of the stiffness, a prediction of the stiffness somehow. But you don't measure the stiffness, so you don't know what it is for real. I mean, it doesn't mean that when you turn on the actuator, you don't know the stiffness. You put a reference stiffness and the actuator makes this. But because the actuator was identified before, and so it closes the loop inside. Also, Manolo this afternoon will teach you how to do some nice identification of the system and to implement a basic control on the actuators. This is part of the lesson of this afternoon. Yes?
This is easier. How you synchronize the two motors, for example, in this case?
In our actuator, we have two independent PID control with high gains, and it works. But depends on the precision you want. I mean, part of the hysteresis, for example, is due also to the imperfect control of the motors. Depending on how much precision you want, you could need for better controllers. For example, when you... Sorry, let's go back a little. If you want to do a very precise control, you probably have to compensate for these torques here on the motors. And now in our actuators, we do it with the integral part, which is, it's enough for many applications, not for everything. But for more advanced actuator, you could think about compensating this. This kind of these terms here are similar to gravity terms on a robot. They are, or to external torques. So, if there are no more questions, I think we are free until lunch. We will be on the back for any other question. We will keep doing troubleshooting for the hardware if you want to install the driver for this afternoon. Okay.